Okay, so this is question 2 of assignment 2, and we were given A, which is a subset of S, an ordered set, and we know that A is non-empty and finite, and A is bounded. So the question wants us to prove that A is bounded in this A is bounded and it's a subset of this ordered set S, and also that inf A exists and is in A, and sub A exists and is in A, right? And we use induction to prove this statement. So you know that A is a subset of S, and A is non-empty and finite. So what does that mean? That means that because A is non-empty, the cardinality of A is not 0 because there are elements in A, and the cardinality of A is less than the cardinality of N, the set of natural numbers, because it is finite, right? And the set of natural numbers N is not finite, right? And that means that the cardinality of A must be equal to N, where N is some value in the set of natural numbers, right? And by definition, A is bounded. Right. Now moving on to prove this part of the statement, we let an arbitrary an be defined as this set here, xi, where let an be the set of elements of xi, where so I is bounded by this value k here, where k is any arbitrary value in the set of natural numbers, right? And also let Pn be the statement that inf f and sub a, sorry, inf a and sub a is in A. Now you just have to prove it for the base case. Uh, oops, let me just change this to n. So an a1 would be just x, right? It would only be one element, right? In the case that an is a subset of S that it has one element, that means inf a is x and sup a is also x, Thus, P1 holds. Right? Now, in the inductive step, we assume that PM is true. And so, then PM plus 1 is also true. Right? And we can define AM as follows: x1, x2, so on, xm. Then AM plus 1 would be the set of AM union with one more element, the m plus 1 element, right? And so because we assume that AM is true, right? So if sub A and inf A are in AM, that means that implies that sup A or sup A m plus 1 right? So if sup A and inf A are in this set here, and we assume that this statement is true, then AM plus 1 would just be the set of AM plus the extra element of X, the m plus 1 element, right? And the X and the m plus 1 element of AM plus 1 would either be sup A m plus 1 or inf AM m plus 1 depending on the ordering of set A. And so, thus, by the principle of mathematical induction, m plus 1 is true. And we assume PM plus 1 is true, then, and we've shown that it's true, then PM is true. Oops, PM is true. And then finally, thus, by induction, Pn is true for all for all n in the set of natural numbers.